Okay, so I'm going to end up pushing the exam forward. So instead of next Friday, it's going to be that following Monday. So I believe that should be the 28th of September instead of the 25th. So I'll change that. I'll put an announcement up on Canvas about that after class today, but we will be pushing that exam date up just a little bit. I'll put some practice exams up later today as well. So you'll have this weekend, next week, and next weekend to kind of look at those practice exams. They'll give you a pretty good idea of the types of questions you'll see on the exam. We'll talk a little bit more about kind of the formatting and everything of the exam next week, but I will get those practice exams up today. And you're also going to have one more homework before the exam. I'm going to post an Excel assignment today that also has a few questions that you can do it in Excel, but really you can kind of do it by hand as well. But a portion of it, the first portion of it, you have to do in Excel. It's going to look very similar to what we're doing today. So you'll have that Excel assignment. It'll be due next Friday, so you have a week to do that. I think there should be plenty of time. Then you'll have those practice exams to start looking over, and then we'll have that exam, not next Monday, but the week after that. So like I said, the 28th, okay? It won't be in, the exam will be kind of online, so that Monday what we'll be doing in class is actually just like an exam review. And then you can take that exam at any point during the day. In fact, I'll probably kind of extend it 24 hours from after when class ends to when you can kind of turn it in. So you could even do it Tuesday morning potentially. Okay. Other than that, are there any questions for me before we jump into things? Okay. The other thing I am going to do, just because we're not having a lot of people show up in class, I'm going to put up another poll. And if you change your mind, I'm going to, same kind of thing as last time. If you plan on attending class, I want you to respond yes to it, however I phrase it. If you don't, say no. That way, if we have a small enough group, I can start to get people in here if they want to be here more days every week, okay? So I'm going to put that poll up. Please answer that by the end of the day on Sunday, okay? All right, so let's jump into where we left off. And as always, if anything on Zoom isn't sounding clear or anything having issues with the video, please let me know. I'll kind of keep an eye on the chat. So I believe where we left off last class was we kind of found these averages. We talked about we're going to use these cutoffs. And the general idea of what we're going to first do is try to build a frequency table. Okay? So the frequencies will basically eventually be turned into probabilities. So we'll have our own joint probability or contingency table like the ones we saw in the slides. So the first thing that we did, this is all we did last class, was we said we can use this Countifs formula. It's going to be a little bit different than how we used it previously in this class. But we want to count the number of observations where the wage differential, this variable that was the wage differential, is $100 or more, and that observation or that industry was the example we have, has a union membership of 10% or higher. Right? So those are the two things we want to check. And we want to count every observation that fits those two criteria. So the first thing we said was, okay, Countifs needs to look through this variable, this difference in earnings variable. So we'll control shift down arrow. Right. Go back up. The next thing that it needed, let me get this out of the way. I'll put it a little bit closer so we can see what it's saying. The next thing we needed was what do you want to check this variable for? Well, we want to check to see if it's $100 or more. So greater than or equal to, and then we'll select that value of 100 that we had up in this cell over here, okay? So that was the first thing we wanted to check. The second thing, and it's now whited over that, but what we wanted to check was whether or not the union membership was 10% or higher. So the second variable that we want to look at is going to be this union member percent. Now we could select it. Oops, I had the wrong key. We could select that variable kind of using our shortcut of Control Shift or on a Mac Command Shift down arrow. But I'm going to show you kind of if I'm working on a laptop, what I would usually do. So I know that the range of data goes from 2 to 736. And I know that this union membership variable is in column C. So I'm just going to type in C2 and then colon through C736. All right. So I want to check that variable and say I only want to count it if it's greater than or equal to, and once again, we have to put these and signs, just kind of the syntax, greater than or equal to 10%. So we want to count all the observations where that difference in union, non-union wages is greater than 100, and where that union membership variable is greater than 10. Okay? So that's what we did last class. So any questions on that before we keep moving? All right. So think about the other one, these other cells. Here I'd want to count it if that difference in earnings is $100 or more and union membership is below 10%. So it's really going to be the exact same equation. It's just that instead of greater than or equal to 100 and greater than or equal to 10%, I want greater than or equal to 100, but less than 10%. So probably the easiest way to do this, right? There's two ways. You could, up in this bar here, select everything there, hit copy, then go over to this cell, go up to that bar, and paste. If you copy paste this way, the cell references don't change, right? So the cell references haven't changed, and I could simply change this to be less than 10%. Now, there's a different way you could do it, which is probably the way I would do it. So I've shown you that way, but there's a slightly easier way. So if I look at this cell, I'm never going to want the range of data I look at to change, and I'm never going to want these cutoffs to change. So what I'm going to do is, I don't think this will, if I select all of it, it'll probably give me an error. I'll hit that F4. Oh yeah, sure enough, it doesn't like that. Okay, so we're going to have to select this in parts. So I select what I want to put dollar signs in front of. I hit F4, or on a Mac, Alt-T, get my dollar signs on all these cell references. Okay. Now I'm going to copy this across and then down. Now it should give me the same value because nothing should have changed. All right. But what do I know? In this cell, what I want to change is I want it to be, is the difference in earnings $100 or more, and is union membership below 10%. So I look at what I have in the cell, and I'll try to get it all in one line. There we go. I actually want to see is this union membership less than 10, whoops, less than 10%. So I change that to a less than sign. In this cell, I want to know, is it below 10% union membership, and is the wage differential less than 100? So here, I would change both of these to less than signs, right? And then the final line to change, I want to know, is it less than $100? So I'll change this to a less than sign, greater than 10%, sorry, greater than or equal to 10%, so I can leave that the same. Now I've got all my frequencies for these different combinations of, really remember what we said last class, this is B complement, A complement. Okay? All right, so we've got these here. Just like with the contingency tables, when we're dealing with actual values, we can add down the columns and across the rows to get our totals. So why does that work? Well, if we think about it, here is every industry where there's a wage differential of $100 or more and union membership is 10% or higher. If I add that to the industries that have a wage differential of $100 or more, but the union membership is below 10%, well, that covers every single industry where the wage differential is over $100, right? So just like with the contingency tables, I can add across the rows to get my total frequencies, right? So there's 221 industries that have high union membership and $100 or more wage differential. There's 184 that have below or low kind of union membership, but still have a wage differential of $100 or more. So if I add those together, that gives me every industry that has a wage differential of $100 or more, okay? So I can copy that down, right? Because that's just gonna be the sum function of the next row. I can then use that sum function to add down the columns to get my totals. right? And now I've got all these frequencies, okay? Now, if I think about this, if I took every industry that had a wage differential of $100 or more, and I added that to every industry that has less than $100 wage differential, that should just be every single industry that exists in this data set, right? So if I add these totals together, I should end up with the total number of observations in my data set, which we said there's a function we can use to check that. If we just use that count function, no count if, just count, and then select one of our variables, it'll count every single cell that has a value in it, and sure enough, we get our total number of observations. Right? So we've done everything correct. It's like a nice, it's kind of a place where you can kind of check yourself. If you get anything other than 735, you know you made a mistake there. Right? For instance, I'll show you an easy mistake that could be made. Let's say I forgot that, oh, this is less than 100 and below 10, and I left my equalities on here. Notice that actually gives me a slightly different value, and now I'm getting more than my total number of observations, because if that equality was on both sides, I might be double counting some of my observations. So I don't want those in there. I was just showing you that to show you how you could make a mistake potentially. All right, so be careful with those equalities. Once we make sure it lines up with what the actual row and column headings are, we see that we've have the total number of observations here, so we at least looks like we've done it correctly. Okay. Any questions up to this point before I keep kind of moving here? Want to see another cell again, or? No? Okay, so we have all these frequencies. If I want to turn these into probabilities, right, it's actually pretty simple, okay? So here I've got, and if I didn't have this, let's say that this wasn't here. I think I included on here, but I'm not sure it would be on your Excel assignment. So I create this frequency table. What I could do is simply copy it and then paste it and then get rid of all my numbers. And now I just have like the format of the table, right? It's just an easy way so I don't have to type everything in again. Okay? But what I now want in here is not frequencies, but probabilities. Well, if there's 221 industries where there's a wage differential of $100 or more and union membership is higher than 10%, out of 735, if I chose an industry at random, what's the probability that it's in this category? Well, based off the data, 221 out of 735. It goes back to where we're almost doing the same thing when we created relative frequencies. Remember, we took our frequencies, and how do we get relative frequencies? We simply divided that frequency by my total number of observations. Right? So that's all we're going to do here as well. Right? We said relative frequencies we can start thinking about as probabilities. Well, now we want probabilities. It's creating them the exact same way. Right? We can think of them as relative frequencies and kind of relate that to things we've already talked about. Now, the problem is if I try to copy this over, right, and do this for every single one, I got a problem, right? Well, why do I have a problem? Well, because I'm starting to divide by blanks, right? To get all these probabilities, I want to take every frequency and divide it by the total. So when I go back here, I want this K9 to keep updating to these different cells, but I always want to be dividing by the total number of observations. So I have to freeze that cell reference for where the total number of observations is. Okay? Once I do that, now when I copy it over and down, just going to be taking, right, the frequency of whatever kind of combination I'm in, right? This cell has the less than 100 below 10% and divided by the total number of observations. Right? So once I put those dollar signs around the total number of observations cell reference, and then when I copy it across and down, now I've got my probabilities. I have my contingency or my joint probability table that I wanted, but I had to first start out finding these frequencies. Once I found the frequencies, it's pretty easy, I think, hopefully it looks easy to you, to find these probabilities because we simply divide the frequencies by the total number of observations. Okay, and if I've done everything correctly, right, this total should be the total number of observations divided by the total number of observations, and so I should be getting a 1 there. Okay. So now we have our contingency table. We can start to do things like we did in class and just use this contingency table. And like, obviously there's a little bit, quite a few more decimals. So maybe just to make it easier, nope, I'm going the wrong way. Maybe I round them to kind of just look nice there to like the second decimal, right? And now this looks kind of more similar to what we were working with in class, okay? So what if I wanted to just get from this table the probability that union membership, and I shorthanded some of this here, so if you want to like type in, union membership 10% or above or something, that's fine. But what's the probability union membership is 10% or higher from this table? Well, the probability of 10% or higher would just be the total, so it'd be in this cell right here. So now, instead of even just like writing numbers down, it's as easy as I know that this probability is in this cell, so this probability is equal to that cell, whatever value is in that cell. I just click on it, and then it kind of displays it for me, right? What if I wanted the probability of being 10% or higher union membership and a wage differential of $100 or more? Well, that's going to be an intersection, right? We have an and, so the probability of being 10% or higher union membership and $100 or more, well, that's just represented by the probability in that cell, right? The top 4 left cells in our contingency table all represent intersections, which kind of, in our typical language, we say intersections as and, okay? So we'll hit enter there. What if we wanted some conditional probability? So this is a little bit more tricky, right? Because when we have a conditional probability, we said, using that multiplication rule, a conditional probability is equal to the intersection of these two events divided by the probability of whatever we're conditioning on. So I'm actually gonna, just so we can read this a little easier, expand that column out. So really what I'm saying here is what I want is the intersection of those two events. So I could say $100 or more and 10% or above. And I'm going to want to divide that by the probability of whatever I'm conditioning on. Remember, what you're conditioning on is what's on the right-hand side of that line. So I'm conditioning on whether or not it's 10% or above union membership, right? So I'm just writing this in just so we can kind of think about how we're going to find this, right? I'm just rewriting this conditional probability as using that multiplication rule as another formula we know would give us the same thing, okay? So if I want to do that in Excel, where's the probability of being $100 or more and 10% or above? Well, the intersection of those two things is right here, right? 10% or higher and $100 or more wage differential. I would then divide that by simply the probability of being 10% or higher union membership, which I know is just the total right here. So all I'm doing is once I have this contingency table in Excel, if I'm asked questions, like I could be just, asked to do these by hand, not in Excel, it's really easy. I'm just clicking on the cells, kind of inputting the values from that contingency table. Okay? So sure enough, it kind of does that math for me, makes my life a little bit easier. What if I wanted the probability of a $100 or more wage differential given that they had low union membership or below 10%? Well, that would be, once again, not that. Let's write it out as the intersection of these two divided by the probability of what I'm conditioning on now. So it's $100 or more, and is it below 10% now? And then I would divide that by the probability of whatever I'm conditioning on, right? So this was the intersection of these two. What I'm conditioning on is on the right-hand side of that line. So is it below 10% union membership? That's kind of the equation that I'm going to want to use. So the intersection of having $100 or more wage differential and below 10% is right here. Right? That's the intersection of those two. I'll then divide that by the probability of having a below 10% union membership, which is just then my total there. And now I'm done. So we can find conditional probabilities relatively easy once we have that contingency table, as long as we can remember that multiplication rule, which is a conditional probability is the intersection of those two events divided by the probability of what you're conditioning on. Okay? And this kind of is interesting, and now we have a result that kind of makes sense. Like, so given that I'm looking at an industry that has high union membership, the probability that their union workers are making more than $100 than non-union workers is about 76%. Well, if I'm in a industry with low union membership, the probability that union workers make more than $100 relative to non-union workers is only about 41%. So the idea being that as that percent of union workers drops, right, there's just more non-union workers out there. The union doesn't have as much power, and so they can't argue for as higher wages. Right? So it's kind of interesting. And if we set everything else up like this, the nice thing about this is, if I then go back and say, well, you know, I kind of define having high union membership as 10%, but that was the average. Maybe I want to really like look at really high union membership, right? So I increase that 10 to a 20 cutoff. Notice because I use cell references, everything will update for me, right? If I play around with this, I could say, well, what's the probability it's more than $150? Updates everything for me, right? I mean, it doesn't update my text here, but it updates anywhere where I was using the cell reference. It updates all my numerical values, okay? But, you know, for this one, we had 10 and 100, so I'll kind of, oh, not 200, 100. So I'll keep it there, okay? But that's kind of the nice thing about cell references is if we ever want to go back and change the cutoffs, it would update all these probabilities for us, okay? Any questions on that? Okay with that? Okay, so that's kind of how we build a contingency table from data in Excel. We can then just got a little more practice kind of answering questions with, you know, some not just A and B events, but some specific events, asking, you know, answering some questions on those. The, you know, first 3/4 of your Excel assignment will look very similar to this, right? I mean, almost identical. Obviously a different data set, but very similar. So as you're working on that, have this kind of pulled up as a template. Once again, if you worked along with me, you have whatever work you did in the blank worksheet, but you also have this completed worksheet over here as well, okay? All right. So we did our Excel example. Here's kind of a review of our probability rules. We've got this multiplication rule, which is what we were just kind of using, right? The conditional probability is the intersection of the two events divided by whatever we're conditioning on. We've got the addition rule we've talked about prior. I don't think we're going to use that today, but here's just kind of a summary. So the next thing we're going to talk about, and I don't know if we'll get through all of this today. I may make kind of an extra video that kind of just completes whatever we start talking about today, so we don't have to pick up on it on Monday. We can kind of pick up on using some binomial examples Monday. But we're going to talk about Bayes' theorem for the rest of the class. Okay? So Bayes' theorem is, you know, we could go through kind of the definitional things. So you start out with some prior that an event's going to occur. You run an experiment, look at the outcome, and then update your prior about what you think that probability is going to be. So maybe ahead of time, I think the probability that something happens is 0.5. But then I run the experiment and I see that, you know, after I run it a couple times that it doesn't happen after 5 attempts. And so maybe I reduce my belief because of what I've seen, right? Now, the context of how we're going to use that, it doesn't really necessarily matter a whole lot. But the kind of setup we have for these Bayes theorem problems will be that we have two states of nature. So S1 and S2. So we can see two things occur, right? So we can think of these as complements as well. So like state of nature 1 could be as easy as like thinking about flipping a coin, right? So it's heads or tails, right? We have two outcomes, state of nature 1 and 2, but they're really complements, right? The complement of seeing a head on a coin flip is seeing a tail, right? So we have these two states of nature. So some other examples, maybe guilty, not guilty, results of different tests. So pregnant, not pregnant, HIV positive, HIV negative, COVID positive, COVID negative, we want to do that. And the events have to be exhaustive, right? So this is just the idea, if I add these two events, the probabilities together, they equal 1. Well, this is the same idea as if I added the probability of an event to the probability of its complement, those add to 1, right? So that's why I said we can think of these states of nature as really as like an event and its complement. We then have some tests that we're going to run, or experiment that we run, where we only see two different outcomes, okay? So maybe I'm interested in, is someone guilty or not guilty? I run this experiment, I get some results. Maybe this is like, go to the jury, and then the jury either says they're guilty or not guilty, right? So a lot of the times, these test results sound very similar to the states of nature. For instance, the state of nature is you literally either are HIV positive or HIV negative. You're one of those two. I can't observe that looking at you, so I give you a test, right? And that test either comes back HIV positive or HIV negative, right? A positive test result or negative. So it sounds very similar, but it's different, right? The test is not 100% accurate. It's just evidence of what the true state of nature is, right? And it should be helpful evidence, right? If I see a positive test result, I think that person probably has that disease, but it's not a guarantee, right? So usually we have these positive, non-positive. So I said last slide, I think I deleted a slide here. But really what we're thinking about is if I see the outcome of a test come up positive, right? So let's say I see a COVID test come up positive, what's the probability that person actually has COVID, right? So my state of nature 1 and 2 would be, do they have COVID or not? I can't observe that directly. I'm not like able to, see that with my eyes. So I run a test and I get that the test comes back positive. Well, there's a chance that they don't have it, that I got a false positive, right? And so what is kind of this conditional probability? Right? So I could think about this instead of COVID, the way I had all this set up is kind of using HIV tests. We do the same thing for COVID tests, but I was looking up some data on it and it's harder to find what the exact like false negative rates are and false positives. So I didn't have actual values to that and I didn't want to just guess. But that might actually be something in that extra video. I just use the best values I find. I'll probably give you an example that looks very similar to what we'll do in class today, but using some COVID numbers. So what's the probability that someone has HIV given that they have a test that indicates a positive result, right? Well, if we rearrange this conditional probability that we're interested in, we could rewrite it as the intersection of these two things divided by the probability of what I'm conditioning on. And don't worry too much about this slide. It's going to be kind of a mathematical proof. By the time we get to the end, that's the formula that we're going to want to use, but it kind of gives some intuition along the way here, okay? So the intersection of these two things would be the probability that if I selected someone at random out of the population, they have HIV and they get a positive test result. I divide that by the probability of the fact they just get a positive test result. So we can think about this as when I see a positive test result, that is going to be made up of two people, two types of people. One, they got a positive test result and they have the disease. That's this, right? But the other component of people that get positive test results would be those who get a positive test result and don't have the disease, right? There's going to be some people in that group of people who just see a positive test result but actually don't have the disease, right? So we can kind of think about our denominator here is all the people that get a positive test result, and our numerator is people who get a positive test result and actually have the disease, okay? So, if we rearrange things, if we use the multiplication rule in the, its other form, right? So I just kind of rearrange these things a little bit. The intersection of these two events could be written as the conditional probability times what I'm conditioning on. Right? So all I'm doing is taking this equation, multiplying both sides by the probability of E, and just rearranging it a little bit, right? Okay. So I now can take this, right? If I had instead written it the opposite way, right? Because it doesn't matter if I have the probability of S1 and E or the probability of E and S1, right? We said the order doesn't matter there. So I could have rewritten it as this conditional probability, but now that I'm conditioning on the state of nature 1, I need to be multiplying by the probability of what I'm conditioning on here. Okay. I know that the probability that I see a positive test result is just everyone who gets a positive test result and has the disease, everyone who has a positive test result and does not have the disease, right? It's going to be kind of a combination. Correct positives and false positives make up everybody who gets a positive test result. So I can rewrite these intersections as conditional probabilities times what I'm conditioning on. I can rewrite this intersection as a conditional probability times what I'm conditioning on. And now if I just plug everything in, so I have these colors that kind of correspond, right? If I plug this guy into the numerator and then this guy into the denominator, right? I'm just substituting equations here. I eventually get that if I want this conditional probability, I could find it using this, right? And this might seem like, why am I complicating it so much? Well, because we don't know the underlying probability that just we get a positive test result back. We typically know the probability we get a positive test result back given that someone has the disease and given that they don't. And so a lot of times we only have this information. We don't directly, are not directly given kind of these probabilities. Right? And we'll walk through an example and hopefully this kind of makes a little bit of sense. Right? But here this numerator is really, what's the probability that someone, state of nature 1, has the disease, times the probability that given that they had the disease, they got a positive test result. So this would almost essentially, we're dealing with probabilities, but you can think about it as frequencies, right? Because think about what we did in Excel. We found frequencies to get those probabilities, right? So we could work backwards as well. So this numerator really represents almost like the number of people who have the disease and get a positive test result. And then the denominator is composed of 2 types of people. Well, notice the first part of our denominator is the exact same as our numerator. So really this right here is still just the number of people who have the disease and then end up getting a positive test result. And then this group of people here would be everyone who doesn't have the disease, right? State of nature 2, but that still gets a positive test result, right? So it's like this total number of people get a positive test result in the bottom of the denominator, and then the people who got a positive test result and have the disease as the numerator, okay? So let's actually put some kind of values to this. So I already kind of mentioned that these state of natures have to add up to 1, the probabilities. What's also going to be true is if I condition on the same state of nature, right? And so this is, notice I left kind of SI here. So you could write in S1s and this would hold, or you could write in S2s and it would hold. But if I'm conditioning on the same state of nature, those conditional probabilities, of the outcomes of the tests, E and E complement, have to add to 1. Here's the intuition behind why. Right? Let's say I had a room full of people, okay? Everybody in that room that say had COVID, I kept in the room and put everybody outside. I got rid of every other person. I'm now only left with people that have COVID in the room. If I administer tests to all of them, given that someone has COVID, what's the probability they get a positive test result? Let's say it's 90%. Well, if that's the case, given that they have COVID, what's the probability that they don't get a positive test result? Well, if we throw out the idea that there's like any inconclusive test, the probability I see a positive test result for those people are 90%. The probability I see a negative test result would have to be 10%, right? That's the only other possibility is that they get a negative test result. And so if I condition on the same state of nature, the probabilities of the conditional probabilities for the 2 outcomes of the test have to add up to 1 as well. Right? And this will help us out as we kind of move forward. Now, if I condition on different states of nature, these probabilities don't have to add up to anything, right? This is essentially someone who has a disease and gets a positive test result, plus the probability that given someone doesn't have a disease, they get a positive test result. These don't have to add up to anything. Okay? In fact, if I was thinking about here, E complement being a negative test result, I know for COVID, like if you can, so given that you have the disease, it identifies it correctly, it gives you a positive test result, a relatively high percent of time, but if you get a negative test result, that's not necessarily indicative that you don't have disease, right? So if you get a positive result, there's not a lot of false positives, right? But there's a ton of false negatives. So if I'm conditioning on different states of nature there, those things don't have to add up to anything. In fact, they could add up to potentially over 100%, right? So that different states of nature, we can't say anything about that, okay? All right, so let's use this HIV test example. This is the one that I actually have some values on. So if you just look at the probability that if I chose someone at random, no other information about them, The probability in America they have HIV is about what, 0.6%, right? So if they have HIV, so if the person is HIV positive, the probability the test records a positive result is 0.999. So very accurate tests, right? If you actually have the disease, it almost 100% identifies it, right? Not quite, 99.9%, but very close. So this would be like, given that someone has HIV, is HIV positive, the probability they get a positive test result, right, is 0.999. The probability that given someone is HIV negative, they get a positive test result or a false positive is about 1%. Okay, these are some of like the actual values. So if I administer a test at random and it comes back positive, what's the probability the person actually has HIV? Okay. So now what I'm dealing with is, given I see a positive test result, what's the probability the person actually has HIV? So if I was kind of writing this out, I could do a probability table from the information that I'm given. So I was told if I chose someone at random, the probability they have HIV is 0.006, which means the probability that they don't have it, right? We said the probability of these two states of nature have to add up to 1. So if I know the probability that someone has HIV is 0.006, the probability that they don't have HIV is whatever gets me up to 1, or 0.994, right? 1 minus that 0.006. So I created this tree to have two states of nature. So here's my first state of nature. Here's my second state of nature, right? And I have to be given at least one of these probabilities. Right? In any problem we deal with that's Bayes' theorems, you have to be given the probability of at least one of these states of nature. Now, to help kind of organize it and make it easier, you don't have to create this tree for every example. I think it helps because now I can think about, on this side of the tree for this state of nature, I have two outcomes I could see for the test, either a positive or a negative result. So given, right, now that I'm on like this side of this probability tree, I'm conditioning on the same state of nature, which is whatever this state of nature is here, right? This is like the HIV positive branch. This is the HIV negative branch. So once I find the unconditional probability here, I can find the conditional probability for the two outcomes of the test, positive and negative, conditioning on the same state of nature, right? So I'm conditioning on whether or not the person's HIV positive, and then I want the probability they get a positive or negative test result. Well, if I go back here, what was I given? Well, here I was told, you know, and I could, probably in a problem like on the exam, I would phrase this a little differently. I would probably write it as something like this. One second. So get rid of, I said it this way before. On an exam, I'd probably write it out a little bit clearer. Given that a person is HIV positive, so anytime we see this word given, you should automatically be thinking about whatever I'm told is the given, that's what goes on the right-hand side of that conditional line, right? So given that the person's HIV positive, the probability that they get a positive test result is 0.999. So when I'm thinking about my probability tree, given that they're HIV positive, the probability they got a positive test result is 0.999. So basically, if I have HIV, the probability that a test will be able to identify that is 99.9%. So given that I have HIV, what's the probability that it doesn't identify that, or that I get a negative test result? Well, it's the only other outcome. We're kind of not dealing with inconclusive tests here. And so we know that the probability of a negative test result would just be, if this is 99.9, this is going to be 0.1%. Or if the probability is 0.999, the probability of seeing a negative test result is 0.001. Okay? And this goes back to the idea of, if I condition on the same state of nature, which I'm doing here, the conditional probability for the two outcomes of the test, E and E complement, have to add to 1. Right? So as long as I have one of those conditional probabilities, I can find the other one. Right? Now, the other information I was given up here is this last guy. So I'm going to rewrite this one too, is kind of how I would probably put this on exam. So given that a person is HIV negative, the probability the test records a positive result is 0.01. Oops, didn't delete everything. So this is probably more how I'd write it, just to make it a little bit easier. I mean, it's really what the other, saying it the other way was saying the same thing. But I always try to throw in that word given just to make it a little bit easier to identify, right? That this is a conditional probability. So given that the person's HIV negative, that's what we're conditioning on, the probability they get a positive test result is 0.01. So that's what we have right here. Well, if I am HIV negative, the probability of a positive test result is 1%. What's the probability of a negative result? 99%, or the probability of 0.99. Right? So now we have everything organized. And the reason why that's important is because once we get to, let me just show you here real quick. Once we get to Bayes' theorem here, if I have that tree laid out, I can find each one of these pieces of information pretty easily in that tree, right? So I've got that tree, I got all my probabilities straight, and here's what I wanted to find. So the question originally was, here's all this information about HIV, false negative, false positives. Given that I go get a test and I see a positive test result, what's the actual probability I have that disease, right? Well, I don't have this. This is one of the pieces of information I was given. But if I rewrite this out in terms of that Bayes' theorem formula, I think I could probably figure it out, right? So here is my state of nature one that I'm interested in. So what I would do if I'm working kind of on this, I would even write, like, here's my S1, and then here's my outcome of the test, E. I know it looks terrible, but kind of giving you an idea. I would just write it right above it, okay? Once I know this is my S1, this is my E, now when I go to write that formula out, all I'm doing is plugging in what my state of nature one is and what my outcome E are. So what I'm really doing there, and for the exam, you'll have a formula sheet. So you'll be able to see, if I can find it here, you'll be able to see this guy right here. So I'll look at this. My state of nature one was being HIV positive. My outcome E was seeing a positive test result. So I then just start filling things in. So HIV positive, positive test result. HIV positive, write it out in the context of my example. That's all I'm going to do there, okay? Once I've done that, I would arrive at this equation. Once I write it out in the context of my example, it should be pretty easy because now look, what's the probability someone is HIV positive? 0.006. Given that they're HIV positive, what's the probability they get a positive test result? Well, I had that written down here, or I could just think about I grabbed it from my probability tree if I had written it out that way. And then notice that first part of the numerator, remember I said is the same as, sorry, the first part of the denominator is the same as the numerator. So it's really just plugging in the same values there. So 0.006, 0.999, 0.006, 0.999. What's the probability someone's HIV negative? We found that was 0.994. And then given that they're HIV negative, what's the probability to see a positive test result? That's just 0.01, right? So I plug all those values in, and now I can find that original conditional probability I was interested in, okay? And this is, you know, this result might seem wild, because if I think about this, what's really saying is if I went out and got a HIV test, or I saw someone comes up to me and they go, I got a positive result on an HIV test. The probability they actually have HIV is only 38%. So why? Why is that the case? Well, if we think about what this denominator is made up of, it's made up of people who get a positive test result and actually have the disease, and then another group of people, which would be people who get a positive test result but don't actually have the disease. But if we think about like something like this, notice the probability someone doesn't have the disease is so high that you're going to get, even if the percent of false positives is low, right? It's only 1%. That's going to end up being a lot of people, right? Even though there's a really low false positive, if most people don't have the disease, right? Think about it this way. If we try to put numbers to it, this is a little bit less than about 0.5%. So like 1.5 million people have HIV, and we'll be able to correctly identify almost all of them, right? So we've got about 1.5 million people here that have the disease. Here, I've got about what? No, it's 350 million people in the US. So we'll just say about 350 million people, right, that don't have the disease, times 1%. So of the people that don't have the disease, we're going to get, if we gave a test to every single person, we end up with 3.5 million people that have a positive test result but don't have the disease, compared to the 1.5 that have the disease and got a positive test result. So anytime we have this like imbalance of most people don't have whatever disease we're looking at, not a lot of people do, excuse me, it doesn't matter how accurate the tests are, we could end up with these kind of crazy results for these conditional probabilities. And it's good that we would know that, right? Okay. Any questions on that before we kind of move a little bit more? Okay with that? Get the chat open. Okay. So it's kind of a wild example. We won't have time to get through this one, so I'll probably work through this example in that additional video that I'll post. Really shouldn't have too much more. I'll go through this. We could do this, well, I'll probably maybe do this problem next week, kind of to end one of our classes. I'll probably also do a COVID example as well. So really the lecture will just be 2 more examples of Bayes' theorem problems. And then next week we'll start out on kind of the last things that we're going to talk about before the exam, which is discrete random variables. So we'll do discrete random variables next week. We'll do that review session on Monday of kind of the 28th, which will also be the day that you then can take the exam. Okay? All right, look for that other Excel assignment as well. I would try to get that done as early as possible so you're not working on it kind of closer to the exam when you should be looking at practice materials. Other than that, also please try to take that poll by the end of the day Sunday, so I can try to get you, those of you who want to show up to class in here, maybe even, I mean, based off the number of people who are showing up, maybe every single day if you want to, okay? All right, have a good weekend.